Our topic for today, and for the next few classes, involves analyzing various properties of functions. And, as always in this class, we'll start with some formal definitions to clearly specify what we're talking about. You are undoubtedly already familiar with functions and with various ways of defining functions. But to talk about functions using the formalisms that we have established in this class, we're going to have to define them slightly differently. If we have a function that maps particular inputs to particular outputs, one way we could think of defining that function would be to exhaustively list all of the possible inputs to that function and what the corresponding output should be. So much like we did with truth tables for Boolean algebra, we could define arbitrary functions by building a table where we have one column with all of the possible inputs to that function and another column with the corresponding outputs. And if we define a function in this way, then we can think of the set of all things that can be inputs to the function, and we call that the domain of the function. And the set of all things in the right-hand column that can be outputs of the function are its image. But the pairing of every input with an output suggests another possible representation, which is to list all of the input-output pairs as a definition of the function. This may seem like a strange way to define a function, but its advantage is that it is closely related to our previous definition of relations. And if we think about the graphical representation of a function that we're all familiar with, we can think of this curve as a collection of xy points. And so when we draw the graph of a function, we are describing a set of pairs, and so we have the same sort of representation. In this case, the curve that I have drawn for f of x equals x squared would correspond to the set of pairs where x and y are real numbers and y equals x squared. So, in fact, thinking of a function as a type of relation is just another way of conceptualizing the ideas about functions we already have. So, let's now use this idea to give a formal definition of a function. So we define a function from set A to set B as a subset of the Cartesian product. So that makes our function f a relation, but it is a relation with a couple of specific properties. The first property is that for every element of the input set, there is some mapping for that element in the output set. So we can call this existence, that there exists a mapping for every input. And our second property is that no input has more than one output. So here we're saying that for every element of the domain, the output is unique. We can't have two different things that A maps to. So let's look at some example relations and think about whether or not they meet the definition of a function. So we have defined f here as a relation from A to B, because it is a set of ordered pairs where the first element comes from A and the second comes from B. And so the question is whether f is a function from a to b. To meet the definition of a function, it has to have the existence and uniqueness properties. And to help illustrate those properties, let's draw a picture. Because our relation maps elements of set A to elements of set B, we can draw it as arrows from elements of A to elements of B. And when we draw the relation as this sort of mapping, it becomes clear that we don't have the existence property. Existence says that for every input, there needs to be some output, and here, 5 has not been mapped to any output. There is no pair in the set describing f that begins with 5, so we don't have the existence property, and so f is not a function. But since f is a relation, we can think about the inverse relation, where we reverse all of the pairs. And we can also ask whether f inverse is a function. If it were a function, it would be a function from the set B to the set A. And if we were to draw the inverse relation, we would do that by reversing all of the arrows from our initial relation f. And when we reverse the arrows, we see that we have 2 outputs for element W, which means that we don't have the uniqueness property. And so in this case, f inverse was also not a function. So now we can build on our formal definition of a function to define certain properties that functions may or may not have. And then we can use those properties to analyze various functions of interest and prove things about those functions. We call a function one-to-one if, for every possible output, there's only one input that can produce it. We call a function onto its output set if, for every element of that output set, there is some input that maps to it. And we call a function bijective if it is both one-to-one and onto. Let's illustrate these properties with a few examples. This mapping is a function from A to B because for every element of our input set, we have exactly one output that it maps to. And this function is one-to-one because there is no element of B that is the output for multiple distinct inputs. But it's not onto because there's an element of B that is never the output of the mapping. This mapping is also a function because, again, every element of A has exactly one arrow mapping it to something in B. And this function is onto because every element of B has at least one arrow coming into it. But we have multiple elements of A that map to the same element of B, so this function is not one-to-one. So in terms of these diagrams, we have a function as long as every element of A has exactly one arrow coming out of it. The function is one-to-one as long as no element of B has multiple arrows coming in. and the function is onto as long as every element of b has at least one arrow coming in. So to have a function that is bijective, it must meet all of those criteria, and so we have exactly one arrow coming out of every element of A, and exactly one arrow coming into every element of B. So when we're operating on sets that are small enough to draw these pictures, we can easily identify whether a relation is a function and whether a function is one-to-one or onto. But often we will want to think about functions that operate on very large or even infinite sets, and so we should think about how can we, in general, prove that a relation is a function or prove that a function is one-to-one or onto. If we have a relation, then proving that it is a function means proving that it satisfies both of the properties, existence and uniqueness. So we go back to the definitions of existence and uniqueness, and we can unravel those definitions in the context of the particular relation of interest. At the end of the lecture, we will prove a theorem that includes proving that a particular relation is a function, and so we'll come back to this proof template then. But before then, I want to build more familiarity with our properties. So let's first think about proof templates for showing that a function is one-to-one or that a function is onto. So here we start with the knowledge that f is a function, and we want to show that it is one-to-one. And our definition of one-to-one said that if we have two outputs that are the same, then the inputs must have been the same. And so we need to prove this implication, and we can do that using any of our proof templates for an if-then theorem. We could use a direct proof where we suppose our hypothesis at the top of the page and reach our conclusion at the end of the page and unravel definitions and use algebraic manipulations in between. We could prove the contrapositive of this statement, that is, the negation of our conclusion implies the negation of our hypothesis. So we could start from elements A and B that are not equal, and then eventually conclude that the output of the function on those elements must not be equal. It occurred to me that up till now I was using lowercase b to specifically refer to an element of the set B, whereas here these elements both belong to the set A, whereas the output of the function on those elements belongs to B, so I've renamed them to x and y to hopefully make that clearer. But then to prove this implication, we also have the option of a proof by contradiction. In which case we would suppose our hypothesis and the negation of our conclusion and use those to arrive at some contradiction that shows that they cannot simultaneously hold. So we have several options for proving the implication to show that a function is one-to-one. But if we want to show that a function is not one-to-one, that amounts to showing that this implication is false, which we do by giving a counterexample. So let's think about some functions that operate on infinite sets, where we will need our proof templates in order to show that they are or are not one-to-one. Here we are defining a function f where the set of things that can be inputs to the function are pairs where the first element of the pair is an integer and the second element of the pair is a non-zero integer, and then the set of things that can be outputs from the function are the rational numbers. So our function of two integers produces the rational number x over y. And our question is whether this function is one-to-one. If this function were one-to-one, then for every possible output, every rational number that could be produced by this function, there must be only one input that could produce it. But that's clearly not the case. We can give a counterexample where we have two different input pairs that produce the same output rational number. So we have two different inputs that produce the same output, which gives us a counterexample showing that this function is not one-to-one. Here we've defined a function whose input set is the integers and whose output set is also the integers. And we again want to know whether our function is one-to-one. To show that the function is one-to-one, we would need to show that whenever we have two outputs of the function that are the same, the inputs must have been the same. So we can do this with a direct proof. So if we have two outputs that are both equal to some integer z, then the way we've defined the function, x must be equal to z over 2, and y must also be equal to z over 2. So x and y are equal, and we've shown that whenever the outputs of the function are equal, that means the inputs were equal, which means this function is one-to-one. Up next, let's think about how to prove that a function is onto. To prove that a function is onto, we have to show that there is some way of outputting every element of b. So we can start with an arbitrary element of b and show how to construct the element of the input set that will produce b as an output. We can also think of this as a set equality proof. Where we show that the image of the function, that is, the set of all things that can be outputs of the function, is equal to the set b. Since we are starting with a function that maps a to b, we know that the outputs of the function must be elements of b, and so one direction of this set equality is trivial. So showing that these sets are equal amounts to showing that b is a subset of the image of f. And the way that we show that b is a subset of the image is we hypothesize we have some element of b and show that it is in this set, where this set is the things that are produced as some output of the function. And so, in fact, this set equality proof amounts to exactly the same thing we have here, where we hypothesize an arbitrary element of b and show how to produce that as an output of the function. On the other hand, if we want to show that a function is not onto, then we need to find some element of b that is never the output of the function. So to prove that the element is never an output of the mapping, we have to prove that for every element of the input set, it doesn't map to b. So let's think about the same functions as before. Our function f can in fact produce every single element of the rationals as an output, and we can prove that by hypothesizing that we have an arbitrary rational number. And we want to show that this can be an output of the function. But that follows as soon as we start to unravel definitions. And so every rational number can be the output of this function. But when we think about g and ask, can every element of the integers be an output of this function? Well, no. This function only outputs even numbers, and so we can pick as our counter example any odd number we like. To show that 1 is a counterexample, we need to argue that there is no input in the set of integers that could produce 1 as the output of this function. We could do that by contradiction. If there were an integer that produced 1 as an output, then a half would be an integer, so we have a contradiction, and so there is no input integer that produces 1 as the output of this function. To wrap up, I want to come back to the idea of a function's inverse and think about when is the inverse of a function also a function, and this will give us an opportunity to try out proving that something is a function. If we have some function f, then since every function is a relation, the inverse function, where we flip all of the mappings, is also a relation. And so we're asking, when is that reversed relation also a function? And the theorem says that a function's inverse is a function if and only if the f that we started with is bijective. So to prove this if and only if statement, we need to show implications in both directions. And for each of these directions, we actually need to show two properties. To prove that the inverse relation is a function, we need to show that it satisfies both existence and uniqueness. And then for the other direction, to show that f is bijective, we need to show that it is both one-to-one and onto. So for the forward direction, we can use a direct proof where we begin by supposing that f is bijective, and we're trying to reach the conclusion that f inverse is a function. So remember that f inverse maps in the other direction of f, so it maps from b to a. And so to show existence, we want to show that for every element of b, it maps to something. And so for a direct proof, we can hypothesize that we have some element of the domain of f inverse, and we want to conclude that f inverse maps b to some element of a. And because f is bijective, we know that f is onto, and we can unravel the definition of onto. But if f of a gives us b, then f inverse of b must give us a. And so we have existence for f inverse. For uniqueness, we have the implication that if we have two outputs for the same input, those outputs must be equal. So let's suppose the hypothesis. And we want to arrive at the conclusion that a and a prime are equal, so that we only have one output for b. And here we can use the fact that a bijective function is one-to-one. Since the function f is one-to-one, that means the only way we can get two outputs that are the same is if the inputs were the same. So since f of a giving us b means f inverse of b gives us a, and likewise for a prime, we have the implication that we want, showing that f inverse satisfies uniqueness. And so with both existence and uniqueness, we have that f inverse is a function. For a direct proof in the other direction, we start by supposing our hypothesis. And we want to eventually show that f is bijective. For one-to-one, we want to show an implication, and we'll use a direct proof. We hypothesize that we have two ways of producing b, and we want to show that those in fact are the same input. But since we know that f inverse is a function, we can't have two different outputs for the same input. And so we've shown the implication for one-to-one. For onto, we want to show that any element of b can be hit by the function. So we'll start with an arbitrary element of b. But then, since f inverse is a function, it produces some element of the input set as its output on b. So when we reverse this, f must give us that element b for some element of the input set. And so we have a way of hitting every possible output, so f is onto. And since it's both one-to-one and onto, f is bijective. And of course, since f is the inverse of f inverse, this theorem also means that the relation f is a function if and only if f inverse is bijective. You might also encounter the terms injective and surjective, which mean respectively one-to-one and onto, and this is the source of the name bijective, that a function which is both injective and surjective is called bijective, but I will try to stick to the names one-to-one and onto. This lecture had a lot of definitions, but in upcoming classes we'll see ways to use these properties to prove much more interesting things about sets and functions.